Ai, boa tarde para todo mundo. Hoje temos a honra e o prazer de ter o professor Igor Shovkovy. Ele é originariamente da Ucrânia e fez o doutorado no Instituto de Física Teórica de Bogolyubov, fundado do cara que fez as transformações de Bogolyubov, etc, etc. Depois ele, como todos nós, viajou bastante. Antes ele foi para os Estados Unidos, Cincinnati é a Universidade de Minnesota. Depois ele foi na Universidade de Frankfurt, John Goethe University. Depois ele virou assistant professor na Universidade de Western Illinois e depois ele se mudou para Arizona State University, onde é professor agora. Alguns de vocês são familiares com ele, porque ele iniciou a série de colóquios de física teórica. Agora todo mundo se está lamentando que, a causa do Zoom e do YouTube, o mundo é cheio de seminários, colóquios e conferências no vídeo. Mas quando a pandemia iniciou, era muito difícil ver se esses colóquios vão continuar. Ele foi um dos primeiros, por quanto eu sei, o primeiro que iniciou uma série de colóquios da física teórica regulares que estão indo via Zoom. Para mim, isso foi uma inspiração, para seminários aqui também. Mas ele é também um dos líderes da hidrodinâmica, da mecânica estatística fora do equilíbrio com a componente chiral, que é de que ele vai falar hoje. Como sempre, se você tem perguntas, é um seminário bastante pequeno, então vai ser informal. Se tem perguntas, me pode escrever, ou senão vai ser no fim. Vou passar o link da lista de presença no chat para estudantes. And Igor, thank you very much for accepting to speak here. Please go ahead.
Thank you. Just a second, I accidentally clicked something. Thank you very much for a nice introduction. I am glad to give a presentation here. I have known Giorgio for quite a long time, maybe 20 years by now or so, and I'm very glad to have this interesting connection. He's always a lot of ideas, and some of the things that I will be presenting today might have been learned from him, at least at some point during my research time. So I want to talk today about the anomalous chiral matter and some related anomalous chiral phenomena that could be realized in different types of physical systems. So I will be primarily talking about the high energy physics, but as I will mention, it also applies to some of the other types of systems that have nothing to do with the relativistic physics. So to start with and introduce the general idea, I probably should start with the concept of the chirality. This is the property of Dirac fermions when they are massless. When the particles are massless, they are moving with the speed of light. And in this case, there is very simple characteristics that we could define. It's called the chirality. It's very closely related to the helicity of the particles when the momentum is parallel or anti-parallel to the spin of the particles that you're considering. If the spin is parallel to the momentum, you call them right-handed. If the spin is opposite, you call them left-handed. You might say, what's the difference between this and helicity? Well, the helicity is actually remains the same for the antiparticles. For the antiparticles, the chirality switches the sign. So basically, for the particles and antiparticles, the holes, the chirality changes essentially when you're considering the states with the negative energy. And formally, by the way, you could define the chirality as the quantum number of the fermions with respect to the chirality operator of the gamma 5 matrix. Now, of course, in nature, you hardly have any massless Dirac fermions, in particular charged fermions, as I will be talking primarily about the charged Dirac fermions. So most of the particles we know are actually massive. So in that case, you might say that this concept of the chirality is useless because it's not a well-defined property for massive particles. Strictly speaking, it's true. However, you could always define something like the chirality, which is nearly well conserved or well defined. And of course, that happens when you're considering the matter in the ultra-relativistic regime. So in the cases when the temperature is much larger than the corresponding rest mass energy, or the chemical potential is much larger than the corresponding rest mass energy, mc squared. Here, I will be using the unit C = 1. So basically here, I'm comparing the energies, but you don't see the C squared next to M because C is 1. Now, of course, when you do have the mass, the chirality will not stay conserved. It will be flipping with a certain rate. And in principle, you could calculate that rate, and parametrically, it goes as the coupling constant squared times temperature times the ratio of mass to the temperature squared. If you have a large chemical potential, you replace the temperature with a chemical potential, and that will give you the flip rate. So if this flip rate is sufficiently small, so the lifetime of chirality is long, then basically you have a nearly well-defined chirality, and in fact, macroscopically in matter. The types of the systems where this might be relevant includes the quark-gluon plasma that you create heavy ion collisions, super dense matter in compact stars, quark-gluon plasma, actually not necessarily quark-gluon plasma, the plasma in the early universe, because when the temperature is extremely high, you have electroweak plasma. You potentially could create sufficiently relativistic plasma in magnetospheres of magnetars, which is made of electrons and positrons. And there are also some chiral effects that might be important. You could interestingly also realize a similar phenomenon in solid state materials. In a class of relatively recently discovered Dirac and Weyl semimetals, you will find that the electron plasma behaves like quasi-relativistic plasma, and there are also many phenomena that I will be discussing here that are relevant for that. And finally, you could create some systems artificially by designing them properly out of cold atoms or out of some other systems, even acoustic crystals made on a 3D printer, which may have somewhat similar properties with the chirality and all of that. So there are plenty of different systems you could arrange like this, and therefore we have to discuss what kind of interesting physics there could be. Before I go there any further, let me give you a very, very brief mention of the relativistic or pseudo-relativistic plasma in Dirac and Weyl semimetals. It will give you at least the general idea why this is a similar system, but I will not discuss the chiral phenomena in this system, just show you that they are realized and therefore can host similar phenomena. So if you consider solid state materials, you will find that they have these very complicated band structures like the one shown at the bottom here. And of course, you might say, what could be so interesting about that band structure that is so complicated? And the thing is that, as was realized already quite some time ago, that among all kinds of quasiparticles that you could create there, that you could observe there, you could actually identify massless Weyl fermions. So the quasiparticles which behave like massless Weyl fermions in relativistic physics. Of course, this has nothing to do with relativistic physics. In relativistic physics, by the way, instead of v sub f, there would be speed of light. Here you have some parameter which defines the velocity of those particles. And such places in the band structures are actually not very uncommon. In fact, they are very common, and there are many, many materials, though suggest some papers with the discoveries of those materials where this is realized in the low energy physics. And the example of those nodes are shown in this bottom right corner panel, which shows that those kind of band crossings could happen at the band crossings. Blue and green dots represent the nodes where the quasiparticles behave like those Weyl fermions. if the Fermi surface is passing sufficiently close to that, you could actually simulate relativistic-like physics with those quasiparticles. So one might say, how often this happens? Well, it happens when the bands are crossing. And of course, we know from quantum mechanics that at the band crossing points, you have the degenerate quantum mechanics. So you might say, aren't they supposed to repel? And therefore, you would never get those crossings and you would avoid this massless or gapless quasiparticles. You could actually study this in general and find that the general Hamiltonian could be represented by a 2x2 matrix. Well, 2x2 because we have 2 degrees of freedom, a particle from upper band and a particle from lower band. So the most general thing will be a 2x2 Hamiltonian, something of that type. And you could find that it's gapless, or there is no that opening of the gap when the energy here doesn't have d sub k, or if it vanishes at some point in the k space. So that's the condition. And since we are working in a 3-dimensional space, you have 3 different values of the momentum, kx, ky, kz. You have 3 different equations for this equation. And in fact, it can be also always having a solution. And therefore, in 3 dimensions, in fact, such situation is very common, in fact. In fact, even in the band structure of regular iron, you have such crossings. The only issue is they sit very far below the Fermi surface and have little observational implications. So, of course, when those bands cross, you could consider the most general crossing point, how it happens. There are all possible terms when you consider simply a Taylor expansion in deviations from that point. This is the most general expansion. One of them is of a trivial nature. It just gives you tilting of the cone. And in the first approximation, you neglect that. You could also see that those parameters, which are defined from the derivative with respect to momentum, they could be diagonalized in the correspond with some orthogonal transformation. And therefore you could, and also assuming isotropy, you could get to that kind of simplest possible Weyl Hamiltonian. In general, you don't have to have isotropy. You don't have to have zero cone tilting. In general, you could still define the chirality of those nodes of quasiparticles, and it can be defined simply in terms of the sign of the determinant of those matrices Bij. So this is very interesting because, in fact, not just the band crossing and the gapless dispersion relations appear in this case, but there is a topology associated with that. So briefly about the topology, you could solve for the wave function in the general case without going into details. I should only emphasize one little detail that is relevant for the topology. It is interesting to consider this mapping going from the momentum to the wave function and consider an adiabatic evolution of the wave function. So think of something like this. If you apply a weak magnetic field to a quasiparticles with that kind of wave function, its momentum will be slightly changing because the magnetic field changes the momentum. If the magnetic field is very weak, you have a adiabatic evolution of the wave function, and you could describe it something like this by using, again, gradient expansion, and you could represent it in the form of this phase transformation, where the phase is determined by the Berry connection. It's a standard trick that you could analyze the mapping with. You could also define the quantity that is a little more physically observable than that connection, the so-called Berry curvature. And the reason is that the Berry connection changes when you apply a phase transformation to the wave function. The wave function is the same physical wave functions with different kind of phases, but that phase changes the definition of the curvature of the connection, but not of the curvature. So this is a definition of the Berry curvature, which is independent of those ambiguities. And if you use this Berry curvature, you could realize that you could introduce a characteristics, topological characteristics of this Berry curvature, the so-called Chern number. The idea is very simple. In momentum space, if you look at this, in momentum space, it looks like a field created at the origin, and this somewhat similar to the electric field of a regular electric charge in the coordinate space. And we know how to use the Gauss law to calculate the charge sitting inside of the given surface through which you have the electric flux coming through. The same can be defined here if you define the flux of this field. Think of it as a magnetic field in the momentum space. Then you could define the flux through any surface that surrounds it, and you will find that it gives the overall sign here as a result. So this is a characteristic, and it's different for different values of the chiralities. Lambda here is the chirality. So the node with the positive chirality carries the Chern-Simon charge +1, negative chirality -1. And that's the topology that is very important for many properties in the studies of this kind of materials. Of course, in solid state materials, there are some constraints on the possibilities of these chiralities. One of the things is that if you surround a certain node with a closed surface, it's the same as surrounding the rest of the Brillouin zone with the oppositely oriented surface, simply because the Brillouin zone in solid state physics is compact. So if there is a plus sign, if you integrate it in one direction, there will be minus sign if you integrate it in the other direction, which means that there is an opposite sign, a node hidden on the other side of the Brillouin zone. That is basically the essence of the so-called Nielsen-Neer theorem, which states that those nodes have to come in pairs of opposite chirality. So this is essentially what leads you to this kind of Hamiltonian for this kind of system, where you have the coinciding or separated two wild nodes of opposite chirality. When they are sitting at the same point, of course, you have the highest symmetry in the model. You have time reversal and parity symmetry preserved. When you split them in momentum direction, with this kind of term, you break the time reversal symmetry. If you move them up and down with respect to each other, you break the parity symmetry. So in the most general case, you have Weyl semimetals with broken both symmetries or one of those symmetries, or Dirac semimetals if you don't break those symmetries. So essentially, this is the general classifications that allows you to talk about the chiral matter in solid state physics. But with that finished, I'm going to actually go to the chiral anomalous effects that are relevant in all kinds of systems of this type. So there are several anomalous effects that exist, and I will briefly describe them so that you have a general idea without going in all the details. So we are going to talk about anomalous chiral matter. So we're not just talking about elementary particles here and there in vacuum, but actually creating some matter out of it. And I will call the matter chiral if it's possible to sustain non-equal numbers of the left-handed and right-handed particles in that system. So in this case, you could consider the evolution of those charges. The sum of the left and right-handed is the total charge in the system. Total fermion number or total electric charge depends what's the interpretation of the particles, and the difference is the chiral charge. We know how the total charge is controlled. It satisfies the continuity equation. The same isn't true for the chiral charge, however, because of the celebrated quantum chiral anomaly. The chiral charge could be pumped into the system by applying a parallel electric and magnetic field. It's actually a very simple phenomenon. Essentially, what it does, it just creates a spectral flow of the particles from the occupied Dirac sea into the particle states with the positive energy, and that's essentially all it does. And that comes along with the chirality production as well. Now, of course, we don't have perfectly chiral particles often, and then we have to introduce the chirality flip process, which will wash away this chirality, and that's the second term with a negative sign. So the bottom line of all of the interesting physics that was discussed in recent years was actually about the possibility of macroscopic effects in such kind of ultra-relativistic matter that are connected to the chiral anomaly. So this anomalous term, which seem to be a purely quantum effect, which, by the way, is not exactly true, can have classical, or I should say macroscopic effects. And there are many different macroscopic chiral anomalous effects that have been proposed in the literature. I would probably naturally separate them in those that are triggered by the external magnetic field, and this is the list of some of them, and those that are triggered by the vorticity. And basically those two are sort of very closely related, and I am absolutely going to leave out the second part about the vorticity driven effects and emphasize mostly on the first three effects driven by the magnetic field. So in order to start talking about that seriously, let's go into one of these effects. The simplest of them is the chiral separation effect, represented by that general formula, but let me give you a brief introduction where it comes from. It comes from the behavior of fermions, charged fermions, in the presence of a strong magnetic field. If you have those charged particles in magnetic field, you will find that the spectrum is given by the so-called Landau levels. There is all kinds of interesting properties about Landau levels, but one of the things that is important for me here is that the lowest Landau level is spin polarized. There are only particles with spin down in that state. And there is a large density of states there, and actually all the other Landau levels, they are different because they have spins up and down simultaneously. So that's essentially all the facts that you need to know to understand what are those chiral effects. So the first one is the chiral separation effect that appears as follows. Imagine that you have this spectrum of particles in the presence of a magnetic field, and you have spin polarized lowest Landau level represented here, and you introduce a non-zero chemical potential in the system. So you fill out those states. Then you would say, what happens? Well, remember that these states, they are negative P3, means that they are moving against the magnetic field in the negative direction. This are moving in the positive direction. And notice that those are left-handed. On the left, they are right-handed. Summarizing everything, you will actually immediately realize that the right-handed particles moving down, left-handed particles moving up, means that you have the chiral current moving down in both cases, because the left-handed particles moving up, ARP is the same as the current going down, just like we do with the convention of the electrical charge. And that's essentially the result for the chiral separation effect. The chiral current that appears is proportional to the degeneracy I mentioned briefly about, times a factor of 2 times mu, how many of this you will fill out. So that formula can be derived without even actual derivation. There is another effect which is called chiral magnetic effect. The chiral magnetic effect could be explained in basically nearly exactly the same way. The only thing is you have to understand what chiral chemical potential means. It actually means that you fill out right-handed states up to mu5 and remove left-handed states up to mu5 in the Dirac sea. So that will give you this electric net current, which is immediately clear because these particles, they're moving in the negative z direction, and these holes, even though they seem to be moving in this direction, it basically means that the states are moving in the positive direction. So basically, this is the picture. So here we have the negative charge moving downwards, positive charge moving upwards, and that automatically means that we have the presence of the electrical current in the presence of a chemical potential. A little caveat here is that, strictly speaking, this is truly non-equilibrium process because mu5 cannot be arranged in equilibrium, and I will leave that for questions if somebody asks. But that, unlike the first one, the chiral separation effect, the second one is truly non-equilibrium process. Now, what does it have to do with the heavy ion collisions? Well, in the case of the heavy ion collisions, actually, you create all the necessary conditions to realize not only relativistic chiral plasma, but you also have very strong magnetic fields and very strong vorticities present in the collision, in the covalent plasma created by the collisions? Well, it's very easy to understand why. The ions, positively charged ions of gold, for example, they will be carrying very large currents. And in the region between them, you could use Biot-Savart or use the linear Rickard potential to actually derive what the magnetic field will be. And you could easily figure out that the magnetic field in this case will be pointing upwards. The most amazing thing is that the magnetic field is the strongest possible you could find anywhere in the universe at present. That's the values of the magnetic field that you could find there, 10 to 18 to 10 to 19 Gauss. You could also create extremely high vorticity, 10 to 29 revolutions per second. It's a huge vorticity. Of course, I should say that even though it's so huge, you could probably have only half a rotation happening actually in the system, but as a matter of principle, the vorticity itself is huge. So I will be primarily paying attention to the magnetic field driven effects, but there are also some that are relevant, that become of relevance when you consider the vortical effect. Now, where do you get chirality in the heavy ion collisions? Well, the quantum chromodynamics that controls the theory of strong interactions is actually giving you that as well. Well, in the case of quantum chromodynamics, because it has the non-abelian nature of the gauge field, you could actually figure out mathematically very easily that there is some abstract configuration space of different types of gauge fields, so different types of gluon fields in simpler language, where they are differing by a certain topological number. In fact, you could consider this configuration and see that when that configuration is realized, you change the chirality in the system. So the chirality carried by the fermions in the background of this field is changing when you have such a configuration. And those transitions, therefore, could actually randomly induce regions with non-zero chemical potential mu5 in a collision. Of course, the mu5 will change the sign from the event to the event, from the collision to the collision. And even in a single collision, you could have several different regions with different mu5. But if you have such a mu5 created, then locally, you could actually argue that there will be chiral magnetic effect induced, that is the current that is determined by the sign of mu5. And it will be in the same direction as magnetic field if mu5 is positive, or in the opposite direction if mu5 is negative. So naively, in the simplest possible situation, you would imagine some picture like this. You have some chirality created in this region, and it will produce the current going, let's say, in the upwards direction if the mu5 is positive, and you will see a little bit more positive charges on flying upwards, a little bit more negative charges flying downwards. And if you saw that in the experiment, you would say, that's it, I found it. Well, the experiment is a little harder than that. First of all, the charges fluctuate. There could be a charge mu5 sitting somewhere close to the surface. It can be relatively easily producing the current, escaping the covalent plasma. It could be deeply inside and it will be hardly escaping. And in the same collision, you could have a positive and negative. So basically, the only you could hope for is to extract this phenomenon statistically. For that, you could consider the correlation between the particles. By looking at the global picture of the collision, you could establish roughly what is the orientation of this reaction plane, and then tracing the charges of the same sign or opposite sign, actually opposite sign blue and same sign red, you could see if there are some correlations that the particles of the same charge tend to go roughly in the same direction, and the opposite sign will tend to go in the opposite direction. So that experiment can be done. You have a lot of statistics. You could actually analyze it, and this is the result. Actually, this is there are two different results from two different papers, and this is not the only. These are not the only results published. And notice that they kind of reconfirm the same statement. If you consider opposite charge fluctuations, correlation, sorry, then you will see that roughly speaking, 90 and 270 degrees add up to 380. The cosine of that is positive. So this is larger than 0. The other one is negative, like 90 plus 90, 180. The cosine is -1. So roughly speaking, it works. What's the problem? Well, the problem is background. In fact, there are a lot of effects associated with the elliptic flow of this plasma that actually mimic the same correlations without the effect. So somehow you have to separate one from the other. And that's why all of these experiments, even though they might indicate this, the signature of CME, they are far from being conclusive. Along the same lines, people were thinking that there is a possibility of yet another chiral anomalous effect, the so-called chiral magnetic wave. And I'm not going to go into all the details, but I thought I would give you at least a flavor of the corresponding physics. And that is driven by essentially the combination of the chiral separation and chiral magnetic effects. And therefore, it's very, very easy, almost for free, to explain it here in the context. So if you are colliding the heavy ions in the central region, you have unavoidably non-zero chemical potential, electrical chemical potential, that should induce a chiral current density running here, inducing opposite signs chiral chemical potentials on the polar regions of the collision, and therefore producing the chiral magnetic effects going upwards here at the top and downwards here at the bottom. And therefore, you will find a quadruple back-to-back correlations where the charges of the same sign go in the opposite direction. So again, how do you extract this kind of signature? Well, one way that was proposed in the literature was related to measuring the ellipticity of the most abundant particles in the collisions that carry opposite charges. The most abundant particles in the collisions are actually pions. So pi plus and pi minus carry different signs, and in fact, they might happen to have slightly different ellipticities. And therefore, if you look at the ellipticity difference, and of course, this picture is highly exaggerated, but essentially it says like this: if the ellipticity for pi plus is this and pi minus is that, so you could consider the difference between the ellipticities. And sorry, seems like one slide is missing. Consider the difference in that ellipticity, and then you will actually see the effect by measuring that difference. So more rigorously theoretically, you could actually describe that in using this equation. So essentially, when you consider the continuity equations for the charge and the chiral charge, and here the change of the current regular electric charge is due to the chiral separation effect, and the change of the chiral charge due to chiral magnetic effect. Solving itself consistently, you will find that there is a chiral magnetic mode that propagates with the velocity proportional to the magnetic field and inversely proportional to the susceptibility, which is something like t squared or so. Anyway, so this is a theoretical description of the picture that I showed you here. And people were looking for this in the experiment. And the experiment seemed to be promising. It was showing indeed this slope that is a function of the charge asymmetry in the system, and the tendency seemed to agree with the theoretical prediction. So you might start celebrating, but before you do, people come and analyze the actual background effects and find that, in fact, the background effects again dominates the signal. If anything, it seemed to be like 93% of the actual result here. So basically, you start questioning and trying to figure out exactly what happens. Now, additionally, I should say that that chiral magnetic wave may be actually overdamped. And here's a very, very brief idea about that last statement. The naive original consideration of the chiral magnetic effect was only emphasizing the role of two different terms in this continuity equation, completely neglecting the effects of, I think it should be highlighted, completely ignoring the effects of the conductivity in the plasma. So if you have the conductivity, the change of the charge could be due to the divergence of the Ohm current. So this is nothing else but the divergence of the Ohm current, which is determined by the conductivity of the plasma. And in the continuity for the chirality, you will find that there is the actual anomaly that cannot be neglected. Notice that I'm not assuming that this is magnetoplasma, magnetohydrodynamic plasma where the electric field is absent, because I have the Gauss's law, and it tells me that the electric fields will necessarily be induced when I start playing with the deviation of the charge density from the equilibrium. So if I have that charge density, I will have the electric field induced. That induces the anomaly, and that induces the ohmic current. And if I solve the problem carefully, I will find that my solution is overdamped. So roughly speaking, my solution is e to the power negative I K0. If K0 has a negative imaginary part, or in fact, in this case, it will be completely imaginary and negative, this will be an overdamped, not a regular mode, and therefore it will die before it starts. So essentially, the paramagnetic wave might be simply suppressed. That was, of course, by the way, it is important that in a weak plasma, a weakly interacting plasma, this conductivity is extremely high, and therefore this condition is always satisfied. You might say maybe in quark-gluon plasma it's not the case, because it's actually relatively strongly coupled, and this can be analyzed, and using the data for the conductivity and susceptibilities and diffusion from the lattice calculations, we were able to estimate when the mode is damped, and considering different temperatures of the plasma, you will find that the region of not super strong magnetic fields, they're actually excluded because the plasma is overdamped. If you consider the temperature higher, this region expands, and for high temperature, in fact, is extremely wide range, and reaching this kind of magnetic field is very difficult. So basically, it becomes kind of overdamped. The only hope is that perhaps lattice overestimates the conductivity of plasma, and if it's much smaller, then maybe there is a chance of paramagnetic wave. So anyway, those two sort of big ideas were nearly shot down, basically because the experiment has large background or because of some theoretical issues. So are there any fresh ideas to look into this, to analyze maybe the magnetic field, to consider if there are other ways of actually considering this chiral effects? So one of them is related to the possibility of having the collisions with different energies. Obviously, when you have different energies, the ions move past each other with different speed, with different energies, they create different magnetic fields. So this way you could tune the magnetic field or modify magnetic field and see how the effect changes as a result of that. Partially, by the way, some experiments have been done, again, inconclusive. The other way is potentially measure the magnetic field directly in some other ways, and then try to calibrate your heavy ion collisions for the chiral magnetic effect better. And again, I was toying with this kind of ideas recently, but again, it's not completely conclusive yet. One of the ideas that got serious traction since 2018 at least was the idea of using Isobar collisions in testing the chiral magnetic effect. The idea is relying on the simple fact: when you are going to consider the Isobar collisions, so the isobars means ions or nuclei that have the same number of nucleons, so same number of the total protons and neutrons, but different number of the protons. So why is that important? Well, the idea is this: if they have the same number of nucleons, total number of protons, neutrons, then basically they will have roughly the same geometry of colliding. So, and the strong forces largely control how the plasma is controlled, how it expands. So naively, you would have the same geometry in the system, but, and by the way, means the same background, but different number of the protons, creating different strength magnetic fields. So the magnetic fields in rubidium will be stronger than the magnetic field in zirconium, roughly by 4 out of 10% stronger magnetic field. So if that is the case, then actually we can have a little bit better control of the magnetic field. At least we would know that there is a difference in the magnetic field here. And on top of that, we assume that the background is the same in both collisions. The signal is stronger. So if you design properly some observables that are based on, for example, ratios of the effects in rubidium versus zirconium, then you could have deviation from a certain unit value or something like that, and that would indicate the presence of the chiral magnetic effect. Notice that this was the estimate for needed number of events, 400 million events. And then the hope was to achieve the precision of about 4% in the data. Now, the corresponding Isobar run was actually completed in fact 3 years ago, over 3 years ago in 2018. By the way, the algorithm for analyzing the data was actually predefined even before the completion and before the start of the analysis. Instead of 400 million, about 3.8 billion collisions were actually done. So it's 2 orders of magnitude higher. Sorry, 1 order of magnitude higher at a given energy. The blind analysis was performed independently by 5 different groups on that data. And they announced the results actually slightly over 4 weeks now ago. So 4 weeks ago, the results were reported in an open online event at Brookhaven National Lab, and the same day the preprint was posted in the archive. And leaving out all the other details, let me just read you the last sentence of the abstract in that report, and it says, no CME signature that satisfies the predefined criteria has been observed in Isobar collisions in this blind analysis. So that might suggest that this is the end of it. There is absolutely no chiral magnetic effect. But actually, that conclusion will be a little premature, and this is the reason. Indeed, there were all this analysis performed by 5 different groups, and it's a blind analysis. So basically, the group performs and finishes all of that before they share any information with the other groups. And essentially, they come with different points here that corresponds to all of those cleverly designed ratios of different observables, like ellipticity in one collision versus ellipticity of the other collision, or the difference between those correlations that I was showing for the chiral magnetic effect. Same charge, opposite charge. Instead of taking each of them separately, you take the difference between them to remove some systematic uncertainties. You could also divide by V2 to remove the background and basically pile that up here. And if any of these points were above 1, that would indicate chiral magnetic effect. In fact, if the chiral magnetic effect were absent, everybody expected the results to be around 1, because in that case, it would mean that there is no difference between zirconium, and rubidium collisions. In fact, surprisingly at first, it appeared that all of these points dropped below 1, which seemed to indicate something completely strange, anti-CME effect, something opposite. But in reality, it's actually not the opposite. And in fact, there is no miracle here. It's just that some correlations were not fully completely understood when the predefined analysis was initiated and essentially frozen before the start of the analyzing the data. The thing is that the multiplicities of those collisions, they are different in different types of Isobar collisions. So roughly speaking, remember I told you that we consider the Isobars precisely to control for the same geometry in 2 different types of collisions? Well, that didn't work out. The geometry turned out to be different for the same geometry of the collision. The multiplicities actually happen to be different. And depending on centralities, in fact, they change. So basically, if you just take the ratio of those inverse multiplicities, then you will find that, in fact, the reference point should be probably this point, which is about 3% below the 1, so 0.97 or so. In fact, if you look at even more this 4%. If you look at some different observables and consider the corresponding V2 effects for the same type of geometry, then you will get this R ratio, which is about 3% below. So depending which of this is better approximating the control for the geometry, you could actually may have a CME effect. Even if you take this inverse multiplicities and assume that it's about 4% below 1, then you will see that all the data will be indicating that the ratio is larger than 1, and this would be the CME signature. Of course, you have to be very careful because this inverse multiplicities here is actually very, I think I put the arrows in the wrong direction. That's why I mixed up. So the inverse multiplicities, they actually might be not fully reliable in this case, simply because there is a non-trivial dependence on the centrality. So how close they pass to each other, how big the ratio of multiplicities in that case, in the case when they are further peripheral collisions. So all of this requires additional analysis. And of course, it was not done in the predefined analysis because all the algorithm for the analysis was frozen in. These points were added in order to provide the context, but essentially, they do not prove that there is CME. And of course, that means that we have to stay tuned until a better study of all of these effects is performed. So that brings me to the summary of this presentation. The bottom line that I wanted to carry over here is that chiral anomaly may have macroscopic implications in various types of relativistic or quasi-relativistic plasma. Anomaly, chiral anomaly, which is presumably one of very subtle quantum effects, may have observable signatures in the quark-gluon plasma, as well as other forms of relativistic matter in some of those contexts that I was discussing earlier. The chiral magnetic effect, which is essentially by default assumed to be the dipole chiral magnetic effect when the charges, opposite sign charges go back to back, can be potentially seen via charge particle correlations in heavy ion collisions. But of course, the data is not simple. It's actually having a lot of background, and therefore one has to be very careful before jumping on the conclusion that this is observed already. The latest Isobar measurements that I highlighted at the end of the talk, they may suggest that there is a signature of CME, despite that conclusion which is stated in the abstract. But of course, we are also not ready to say that it was observed, because there are still a lot of subtleties how the multiplicities work and how they affect all kinds of observables. In retrospect, I think one might even say that these Isobar collisions were not such a benefit at the end of the day, simply because that control for the geometry that everybody was striving for didn't work out. In fact, perhaps the energy scan of the collisions might be just as useful in analyzing the chiral magnetic effect. Chiral magnetic wave, I didn't really discuss too much about it, but I wanted to at least mention that there is, again, a way of potentially measuring the signatures of the chiral magnetic wave, and those data that exist, they suggest that the background is dominating the observables, and not clear if this is realized in nature. Also, there are some theoretical issues with the chiral magnetic wave that have to be overcome before we take it seriously. And finally, last but not least, signatures of CME are tested and are observed routinely in Dirac and Weyl semimetals. Many of those observables, I should probably say, are still indirect, but those systems are very easy, often much easier to control than heavy ion collisions, and therefore, as a matter of principle, it might be also beneficial to test this kind of effects in condensed matter physics before we understand them better and generalize to heavy ion collisions or flow-glowing plasma. And with that, I think I will stop. I'm done with the main part of my presentation.
Thank you very, very much. Any questions? Raise your hand or just speak up. Anna.
Hello.
Hi,
Can you
Anna.
hear me? Hello, how are
Yes.
you?
Yes.
So thank you for the talk. I think we're having now the annual meeting of the Brazilian Physical Society. I think more people would be present if it was not for that.
Yeah.
So I escaped from that to come here. Regarding the difference in multiplicity that was observed in Isobar collisions, is that because of the difference in mass for neutrons and protons, or what?
No, I don't believe it is due to that, actually. My understanding is that because of the, let me see, I'll go to this picture. The thing is that this naive picture, it kind of assumes that the neutron skin depth is the same for both nuclei. Apparently it's not. So rubidium, I believe rubidium is a little more swelled up. So essentially what that means that we do not have a perfect match of the geometry to start with. So for the same exact impact parameter, the multiplicity is different in those two collisions. But it's not because of the tiny difference between neutron and proton mass. At least that was not the expectation.
Hotspots and.
But then it may be something related to charge, or they have no idea.
Well, yes, the charge of course does change the property of the nucleus, and I guess that what makes the nucleus perhaps more swelled. But somehow the neutron skin becomes also different in those two. Since I didn't really do the structure calculations to actually study the detailed properties of this nuclei, I kind of only repeating the general statements that I see from the literature, but essentially that seemed to be the idea. That because of the different composition number of protons and neutrons, essentially the geometry of the nuclei are different. Even actually something as ellipticity of the nuclei apparently are different by 1 or 2%. But that is a small effect which people knew about. What was not clear is sort of the overall size and how it is important. And I don't know if, for example, if you take different type of isobars, if that is better or worse. But this is one of the unknowns. The good thing is that experimentalists can actually analyze that purely empirically by using the centralities, by using the impact parameters, and they could actually consider those multiplicities, and that's what they measure. So those last points, they are not theoretical, they are actually from the experimental measurements, those multiplicities. So we do know experimentally that they give us different multiplicities.
Okay. And I have another question. Do you know if they have, I mean, I know they're not interested on that, so it's not in the paper, but do they have other kind of data, for example, for direct photons comparing from one collision to the other? I mean, to have information about magnetic field independent of
I don't think the isobars,
effect.
I don't think they did measurements for the isobars for that. So I haven't seen, let me put it this way, but I don't think it exists.
How many days of data was the isobar? Was photons in it?
It's a lot, actually. It's actually at least several days, I believe. maybe several weeks of running. The thing is that apparently some other runs have been canceled and they got more beam time.
I see.
So they got this 3.8 billion points or data collisions, sorry, because apparently my understanding is that they got a little bit more runtime, beam time than expected.
Okay.
Yeah, it would be interesting to know if they have more data.
Yeah.
Yep.
Well, if they have that, I don't know if they would be interested in analyzing it, but I would be interested.
Well, as always with the experimentalists, if you make the case interesting enough, somebody could bite it and could start looking into that. So I think it's a matter of making a good case.
What is the photon observable sensitive to magnetic fields?
Well, the ellipticity of the photon emission is observed. By the way, the ellipticity of the photon emission is sort of an active area even in the other experiments. And the way I see it, people are pushing for lower and lower PTs for the photons. So in the future, I wouldn't be surprised if we get much better data for the photon.
It's a puzzle. It's still, I mean, the fact that photon V2 is the same thing as the hadron V2 is still a puzzle. Yeah.
It is, but some people admit it more as a puzzle or as a bigger puzzle. The others kind of think of it as a little puzzle, depending on who you're talking to. But yeah, absolutely.
Sure.
They do appear abnormally large.
Yeah, there is contamination from the case. Yeah.
Right. Well, but then again, it's such a mass. If you look into detail, there are so many different sources of the photon emission that it would be kind of also naive to say that here we have plasma magnetized done. That's so far from the truth.
Sure. I have a question that, I mean, you said something that I would like you to expand on, because I think this is sort of, I never thought about this, and this could actually be a huge thing. You mentioned, of course, mu5 cannot be defined in equilibrium.
Yep. Yes.
Can you expand on that?
Yes. I don't think I have the actual equations that I wanted to show. Let me see. Do I have the Maxwell equation anywhere? Maybe I don't. Okay, so unfortunately, I don't have the slide that explains that, but I could give that explanation very easily. So if you write down the set of Maxwell equations with the chiral magnetic effect, this formula included in the Ampere's law, then actually you could immediately find that the equation for the magnetic field is unstable. That system of equation produces a growing chiral wave with the helical magnetic field with a given helicity determined by mu5 that is growing in time. So essentially, it's a matter of, this is, by the way, if you are familiar with the inverse magnetic cascade that people were utilizing for early universe, Dima Harzea was analyzing this in the context of early universe. Then basically they say, if you start the evolution with the non-zero chemical potential mu5, you will turn that energy into magnetic helicity in the form of magnetic modes. So if you have stochastic mu5, then of course this magnetic modes will be also stochastic, but the scale on which they are roughly uniform will be growing. And this grows dynamically, but the seed of that is mu5, and the momentum that is characteristic for the growing mode is something like alpha over pi mu5. So all the modes with those momenta, low energy momenta, and therefore long wavelength, they will start growing, and they will eat up all mu5 until it's gone.
I'm shocked that this is sort of not widely, you know.
It is widely, but in the context of heavy ion collisions, we don't have enough time for anything like that. We don't have low energy momentum for developing that. The momenta will be very small. In core-blown plasma, they would not even fit within the collision.
Let me sort of ask a philosophical, if you want, question about this, because this is something So mu anything, we teach statistical mechanics 101. Mu anything is a Lagrange multiplier which maximizes the entropy for a conserved quantity.
Right.
And entropy is an area in the first hand-wavy lectures of statistical mechanics 101. Entropy is the area of phase space which, you know, under certain conditions, you approximate the ergodic limit and the area of phase space is maximized. And this is where, this is why we perform this operation of maximizing. I mean, what you just said is that this whole edifice falls apart for mu phi.
No, actually, mu phi is simply not equilibrium physics. So you cannot really use this mu phi as a Lagrange multiplier in your action or Hamiltonian. It's actually here, it's really used as a representation of this out of equilibrium chiral charge present in the system. So if you ignore that instability, if you ignore that this is not self-consistent, then you could sort of adiabatically deal with it as if it were, but don't take it literally as a chemical potential. It's not. The corresponding charge is not conserved. The corresponding system is not even stable.
I mean, when you talk about scale separation and some scales being too slow, I mean, I'm studying this now. This is why you have these
let me see. In a closed system, in a closed finite system, though, in a closed finite system, you could have actually the conserved combined helicity chirality, and you could introduce something like a conserved total charge, which includes not only the chirality from the fermions, but also the chirality from the gauge field, sort of like extending and introducing this Chern-Simons term together with the chirality. And then if you choose a compact system with certain non-contradictory boundary condition, you could define this conserved charge. In that context, you can, and in that case, you will have equilibrium system with certain small but non-zero mu phi. This will be sort of that barrier below which wavelength we don't have any more phase space, and you would have some small non-zero chiral ball present there, but it will be sort of inversely proportional to the size of the system.
I mean, well, the thing is, I mean, you were talking about the fact that it's too slow for these instabilities to grow, but in other contexts, you have people arguing, and I believe these arguments that plasma instabilities completely screw up any scale separation. You know, you have classic, okay, this is electromagnetics, so you have
well, the thing is this, even in hydrodynamics, you have cascades and inverse cascades. Of course, in regular atmosphere, it's three-dimensional, you have mostly cascades. In a two-dimensional, like shallow water things, you could find some inverse cascade phenomena unrelated to magnetic fields, to the vorticities and stuff. But the same is with the plasma. If you have usual three-dimensional plasma, it will show the so-called cascade when the magnetic field fluctuations happen on ever shorter distance scales. But this mu phi could give you this transient state, while the mu phi is eaten up, the inverse cascade is happening. And plasma physicists, they're actually simulating this more or less rigorously, including all kinds of subtle effects that I wouldn't be able to capture with pen and paper.
Okay.
So if you wish, it's a transient phenomenon until you have mu phi. So first of all, you have to create a source of mu phi. Where do you get it from? In the early universe, there are speculations that certain processes with certain processes that separate, break left-right-handed symmetry. If you have only left-handed leptons, for example, you may have certain processes that temporarily will lead to a non-zero mu phi. Apparently, that mu phi is not that large, but there are some other models where they say it could be larger. In QCD, in this heavy ion collisions, we argue about this essentially aileron or instantron type of processes that could again create mu phi locally. And obviously, all of those processes are far from equilibrium.
It's a fluctuation.
And whatever they lead is only transient.
In heavy ions, it's a fluctuation. It's basically...
It's even a fluctuation, right?
Theta is zero on average, but in the region of quark-gluon plasma, it's away from zero. Could be negative or positive, depends on, you know.
Yeah.
So it's
you just count how many of those you will find and where they are. So they're also weighted by their proximity to the surface of this plasma fireball. I mean, I don't know how much you can trust those models, let me be honest, but I mean, that's the general idea.
It's just that what you said is that there is nothing like a flux. I mean, in approximate equilibrium, you have a fluctuation dissipation theorem, and in hydrodynamics, there are some subtleties, but you know, you have a particle bumping around and fluctuation. What you said is that for mu5, nothing like that exists.
Right.
There is no fluctuation. There are fluctuations, but dissipation kind of goes in the wrong way.
Yeah. It's true.
Because I need to think this over.
It's actually totally asymmetric to compare chiral separation and paramagnetic effect, because one of them is perfectly fine, and by the way, it's not contradicting to anything in equilibrium. So this one, by comparison, is perfectly fine. And the reason it's perfectly fine is that actually the chiral current density could be actually reinterpreted as the magnetization that could perfectly exist in equilibrium.
Of course, that's ferromagnets.
Exactly.
That's
so
the equation
this one is nothing.
Yeah.
And the other one is truly different.
Yeah. No, I understand. I mean, yeah, this is the mean field theory of a ferromagnet, written in a slightly different way.
Basically, it's pure magnetization. For the massless fermions, it's a little tricky. In a finite box, I was looking into this. In a finite box, you could consider like right-handed motors move to the one direction, left-handed to the other direction, and it's J5. However, on the boundary, which breaks chiral symmetry, it's actually perfect reflection without spin flip. So actually, it's nothing else but a reflection from the boundary, standing wave, if you wish, of magnetization. That's it.
Okay. Yeah, the other one is new. Just the fact that it creates an instability that eats it away is something I didn't know.
Yeah.
Anyway, more questions. Yeah, this is...
Students, anybody?
Alguém? Perguntas? Don't be shy, não seja tímido. Temos 7 pessoas aqui.
We were all students at some point.
Yeah.
Still are.
Okay, so I'll ask another question if nobody will ask. It's related to what you're saying. So I mean, we always say that in heavy ions, we need to analyze event by event, otherwise a possible paramagnetic effect is washed out. But in one event, so from what you're saying, you can have domains where, let's say, this mechanism driven by sphalerons is going on, but you can have many with different chair numbers, and in average, it can be 0. So is there any estimate, simulations or anything that makes us to believe that in a single event, it can be different from 0 in average?
Yes, there are simulation, and I wonder if I included any of those references. The DNL people, they actually did this simulation. They even have a picture of this like collision region with the fluctuating charges of positive, negative chirality. And generically, it's really just looks random. Yeah, people did this. I think who did it? I'm trying to remember. Bjorn Schenker, perhaps, did it. Sorensen, maybe. I don't remember actually. No.
But I
forgot. I could find the references, but there is one paper with Raju.
I think
The
Anna is
gradual, there
asking
is,
for a
sorry, go
different
ahead.
thing. Yeah, I think Anna is asking for a different thing, which I don't know if I understand correctly, but it's you take the effective theta and you calculate the width of its correlation function. Is that what you're asking?
Yeah, I'm asking because I mean you cannot have you can have theta in domains, not in not in your true minimum. So you have to have it in small domains. So you can have many domains with.
That's exactly what they look for. What is the configuration of those domains? If you were asking about that, so there were simulations
that's what I'm
where.
asking. Yeah.
So
and then they find something different from zero in average.
Well, not on average. Usually not on average.
Because in one event, I mean, talking about one event, you see the average of the event, of what is happening in the event.
I believe in one event, on average, the difference between the two chiralities is something like 2% of the fluctuations. So roughly speaking, if you have a fluctuation of water 1, the slightly more positive or slightly more negative is like 2 parts in 100. So it's actually very, very rare to have non-zero average. But so, nevertheless, the effect is still could be non-negligible because, first of all, you reduce the phase space a little bit by the geometry. So roughly speaking, those regions closer to the boundary, they essentially have higher weight because the corresponding particles will escape without much diffusion. But the simulations are essentially all of these stages exist. The simulation of the formation of these chiral domains, how they are distributed. There are some simulations of that. Then how this distribution of these domains then affects the chiral magnetic effect in the geometry of heavy ankylosis. There are also some simulations of that.
So even if you have like equal numbers of +1 and -1, I mean chair number, the way they are distributed
could give you slightly non-zero result. Yes.
I see. Thank you.
I guess it's like, I mean, it's throwing coins and measuring the difference between head or tail, and the optimal is if you have like roughly 10. If you have too few, you don't see anything. If you have too many, you don't see anything. But if you have if you have 10, you'll see something. Yeah, that's the way it was. Yeah.
But then again, notice that perhaps one very important thing, the sign doesn't really matter. The thing is that all the observables actually are parity even.
Of course.
That's why we have such a big background. Because the fact that it's, let's say, μ5 positive or negative, it's basically like positive charge goes this way, negative that way. But you do not distinguish in this correlator. You only consider the track of same or opposite charges. If they go same up or same down, you cannot distinguish. So strictly speaking, none of the actual observables are truly parity odd.
Yeah. Yes, of course.
So that further kind of diminishes the value of this observable in a way.
Yeah. Well, no. There are proposals to construct odd parity observables with polarization, right?
That is possible in principle. I'm not sure I've seen the actual proposals how to do it.
Lambda polarization is measured directly. I mean, well, you correlate polarization with momentum and
but can you correlate it with the direction of the angular momentum of the collision? I don't think you could distinguish up or down. Can you?
Yeah,
maybe you can.
Question.
I don't know.
You can. No, maybe you can, because with in fact that you can, because there is an event plane measurement that distinguishes reaction plane up from reaction plane down. You look at the up-down asymmetry far away at the beam, and that would do it. You see what I mean?
A 0-degree detector can tell you. Maybe, I don't know. Anyway, all of these observables that I was telling today, they are actually parity even.
Yeah.
So in
Yeah.
fact, that's why fighting for this background is such a big uphill struggle.
I mean, the difficulty with lambdas is simply that there are very few lambdas. Yeah. And this is a correlation. Yeah. More questions? I will stop recording in case I learned this from